We're going to talk about some definitions of graphs. We're going to model using graphs, and then eventually we're going to solve some problems in mathematics. Graph theory is an entire branch of mathematics. It's like numerical analysis and topology and algebra and analysis. There's all these different branches of mathematics, and graph theory is just one of them. Okay, so here are our tools that we work with in a graph. The first thing is the definition, and a graph consists of a finite set of points. These are called vertices, and this one has a graph with 5 different vertices. The singular of vertice is vertex. So 1 vertex, 2 vertices. And then the segments that connect the dots, those are called edges. So here's an edge. If you have an edge that starts at 1 vertex, and where's it going to go, and it comes back and ends at the same vertex, we call that a loop. And it looks like a loop. So edges and vertices make up our graphs. So how many vertices do you see in this picture? They usually label them. Vertex A, vertex B, vertex C, vertex D. Yeah, now even though these 2 edges it looks like they intersect there, but there's no dot there. There's not a vertex. So it might look like, you might think that they're going to intersect in a point, so therefore there has to be a vertex there. But no, I mean, this could be a 3D shape where this edge goes above this edge. So 4 vertices. All right, now go count the number of edges. How many edges are in that? And remember that a loop is an edge. Edge AD, edge DB, edge BC, loop CC, yeah, that's an edge, and then AC. So 5 edges. Yep. Some of your problems, they're going to ask you to do a model draw a graph that looks like this, that models different scenarios. And the first scenario is a city map. Here's a city map right here. And it's hard to tell, but these 3 islands are in between the mainland, the south side and the north side. And then here's the river. And these 3 islands are inside the river. And you got these bridges as well. There's a bridge connecting Island A with North Metroville. Here's a bridge that connects Island A with Island B. Here's another bridge that connects Island B with Island C. And then it looks like there's 2 bridges going into South Metroville from Island C. And it doesn't look like there's a bridge from Island B up to North Metroville. And it doesn't appear that there's a bridge from Island C up to North Metroville. So it says we have 5 bridges, 1, 2, 3, 4, 5. And it says to draw a graph that models the layout of Metroville. So we're going to let land masses equal the vertices, and we're going to let the bridges be the edges. All right, so I'm going to try to put them in the relative position. Here's one landmass up here is North Metroville. I'll just call it NM. And then you have the 3 islands, Island A, Island B, and Island C. That's another landmass. And then you've got the South Metroville down here, which is another landmass. Since there are 1, 2, 3, 4, 5 land masses, there are 5 vertices. We also have 5 bridges, and the bridges will be edges. So we're going to draw an edge whenever there's a bridge connecting 2 land masses. So for example, here's a bridge that connects North Metroville to Island A. So we're going to draw an edge going from North Metroville to Island A. There's a bridge connecting Island A and Island B. So we'll put an edge between A and B. There's a bridge between Island B and Island C. So we'll put an edge between B and C. And then there is a bridge going from Island C to North Metroville. There. But then there's another bridge going from South Metroville to Island C that is different than this bridge. So to denote that, we'll just come back this way. And now we have 2 bridges going from Island C to South Metroville. And there's the graph that models the situation. We can also model a map based on bordering relationships. So in the states, we will let them be our vertices. And then for the edges, we're going to draw an edge between 2 states, between 2 vertices, which are states, if they have a common border. So it would look something like this. We have Montana and Wyoming and Colorado, and just kind of coming down in here. And then we have Idaho and Utah. 5 states, 1, 2, 3, 4, 5 vertices. All right, now, if 2 states have a common border, we're going to connect them together with an edge. So we'll start up here at Montana. Montana has a border with Idaho. So we're going to connect Montana with Idaho. Here is Yellowstone National Park. Right there, Wyoming. Great place to visit. Montana has a border with Wyoming. So we'll connect them together. Montana does not have a common border with Utah. Montana does not have a common border with Colorado. So there's no edge connecting Montana to either of those 2 states. All right, let's go over to Idaho. We've already got the edge between Idaho and Montana, but you can see this border on Idaho and Wyoming. So Idaho and Wyoming are connected together because they have a common border. Idaho also has a common border between itself and Utah. So we're going to draw an edge between Idaho and Utah. Colorado has a common border with Wyoming and with Utah. So with Wyoming and with Utah. And finally, Wyoming has a common border with Montana, with Idaho, with Utah, and with Colorado, with all of them. So since this Wyoming has a common border with Utah, we also have to add this one. So here's a graph that would model this bordering relationships, they call it. So modeling situations. Okay, so the next one is to model a floor plan of a house. And it has 4 rooms. And so when we model something like this, the rooms will be the vertices. And then the edges will exist if there are any doors that are connecting rooms that allows you to go from one room to the next. Now, the only deviation from this is that E is considered the outside. So E is the outside, and I'll put it in quotes. It's also considered a room. It's the outside room. So it's not really part of the house, but there are doors to the outside. Like right here is a door from room B to the outside. So E is not just here, it's all this around here. All of this outside. E is just the outside of the house. So we have room A, room B, room C, room D, and room E. So I'm just going to kind of write down those 5 rooms kind of in the same position where they're located in the house. Yes. And then we just go room to room and find out where the doors are. So here's A. It doesn't have a room to the outside, but it does have a door that connects it to B. So we're going to draw an edge connecting A with B. There's also a door connecting A and C. That takes care of A. For B, we've already got the door connecting A and B, so we don't have to redo that one. B is also connected to D through this door. And B is also connected to the outside, and the outside is E. So there it is. So the number of doors leaving room B are 1, 2, 3. 1, 2, 3. The number of doors leaving A, 1, 2. Number of edges leaving A, 1, 2. And then C. C has a door to A. We already have that doorway identified. And then C also goes to D. And finally, room D. D goes everywhere. D goes to C, D goes to B, and then D goes to the outside in 2 different ways. So D is going to go to the outside, E, there, and then there. There are 2 different doors, so you have to indicate that with 2 different edges. Now I chose to go this way, but you could go the other way if you want. I suppose you could go right straight this way, but it messes up the graph. And when you cross edges like that, you want to think that there's another vertex there. The point is here that we can have completely different correct graphs. There's lots of different ways to draw this. So D has 1, 2, 3, 4. 1, 2, 3, 4. E has 1, 2, 3. 1, 2, 3. A has 2 doors. C has 2 doors. D has 4. 1, 2, 3, 4. All right, so modeling, and this one is kind of the last one that we'll see. This is draw a graph that models the street of the neighborhood walked by the mail carrier. Use vertices to represent street intersections and corners. Intersections, intersections, and corners. So those are the vertices. And use 1 edge if streets must be covered only once, and use 2 edges for streets that must be covered twice. All right. I don't know if you can see this or not, but these little lighter things in here, these are homes. Homes, 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 and homes. And then you got homes on the outside here, the outside here, the outside here. But when someone delivers the mail, if you live in a subdivision, a lot of times they don't just cross the road and get the houses in order on both sides of the road. Usually what they'll do is they'll go down and they'll deliver the mail on one side of the road, and then they'll come back and do it on the other side of the road. And that's particularly important if you have a busy road, right? So we'll start with these 1, 2, 3, 4, 5, 6, 7, 8, 9 different vertices. Try to make them bigger. So the intersections in the corners, you know, it's not too difficult to model those. What's a little trickier is where the houses are located. Okay, so let's start here. You can see the houses up there, but there's no houses on this side. So there's one edge that needs to be there between this vertex and this vertex. Same thing here. Houses are on this side, but not on this side of this street. I think these are buildings here, houses, and these are buildings, and I think you have buildings over here as well. So I think on the outside, it looks like there's houses on just one side of the street. And then for all of these roads in the middle, these streets in the middle, there are homes on both sides of the street, both sides of the street, both sides of the street, both sides of the street. And because of that, we are going to connect, walk down this way and then back, walk down this way and then back, walk down this way and then back, and then walk down this way and then back. And we're going back and forth because there's homes on both sides. So here's what this graph would look like. One way for this graph to look this way. All right, so we've modeled several different kind of real world scenarios, 4 different ones in fact, using graphs. That is, using edges and vertices. And I think most of ours also, we didn't have even a loop anywhere, but they'll be coming up. Okay, so we're going to get into more definitions. Some of the mathematics that we do depends on the degree of the vertex. So the degree of the vertex is the number of edges coming into a vertex. And usually we'll just write the degree next to the vertex. And based on the nature of these vertex, we can draw some graphs. So let's just go around and find the degree of each vertex here. This vertex up here, you have one edge coming in here and another edge coming in there. So there are 2 different edges. So that vertex has a degree of 2. Now this one here, if you just go all the way around the circle, you can count them. 1, 2, 3, 4. There are 4 edges that come into this vertex, so its degree is 4. This one here, as you go all the way around, you're going to hit 2 different edges, so the degree is 2. All right, let me check to see if you're following this. What's the degree of this guy in the middle here? Go ahead and enter it into the chat box. That one. What's the degree? And label the other ones as well. Okay, good. Yeah, so if you go around 1, 2, 3, 4, 5, 6, 7, 8. So yeah, that one right there is degree 8. And if you notice 2 and 4 and 8, those are all even numbers. We call those even vertices. So 4, 2, 4, 2, and 4, all even. And this one, we have 2 and 2, 1, 2, 3, 4, 1, 2, 3, and 1, 2, 3. So a 3 is an odd number. So this graph has 2 odd vertices, a 3 and a 3, and it has 1, 2, 3 even vertices. What's important to note is that they have 2 odd vertices here. These are all evens. All right, another definition, the last definition in this group here is that we can talk about an adjacent vertex or vertices. An adjacent vertices is a vertex that can be reached from a beginning vertex. It can be reached with an edge. That is, you don't have to go through 2 or 3 edges to get to another vertex. So we would say that vertex D is adjacent to B because you can reach B with one vertex or with one edge. D is also adjacent to A because you can reach it in a single edge. But D is not adjacent to C because there's no edge connecting directly D to C. If you wanted to go from D to C, one path you could take would be to go up to A first and then down to C. But you have to go through an intermediate vertex in order to get there. So therefore we would say D and C are not adjacent. Similarly, D and E are not adjacent. Yeah, the only other thing I would mention here is that if you have a loop, the way you count that degree is you have 1 degree leaving the vertex and 1 degree entering the vertex. So a loop is going to count as 2 on the degree. And then you have this degree, this edge, and then this edge. So the degree of E in this picture is 4. The loop counts as 2 different edges coming in. All right, so you're getting all the definitions of graphs in this section. And then the next 3 sections that follow will use these definitions. So we have paths and we have circuits. So a path is a sequence of adjacent vertices and the edges containing them. It says, although a vertex can appear in the path more than once, an edge can be part of the path only once. So we don't want to do, in a path, we don't want to do any backtracking along paths. So let's identify the path indicated by these arrows. So let's say that we start right at A, and then we follow the arrows. The way that we would denote the path is, all right, so we're going to start at A, and then these arrows indicate that we're going to go, and so the next place we end up with is B. And then if you follow the arrows from there, you're then going to go down to D. And then if you continue, you're going to go to E, and that's it. That's where it stops. So this is one of the paths. You don't have to, you know, in a graph, you don't have to cover every single vertex or every single edge in general, but this is just a path. There are lots of different paths that you can identify. G, F, E, D, B, A would be another one. But this here is not a path. Well, let me give you one and you tell me if this is a path or not. All right, is this a path or is this illegal? C, D, E, D, B, A. Legal? Is this a path or is this not a path? Okay, let me go back to the definition. A path is a graph, is a sequence of adjacent vertices and edges connecting them. Although a vertex can appear on the path more than once, an edge can be part of a path only once. So we will allow to visit the vertex more than once. So here we're visiting D once, but we can't retrace a edge. So this in fact is a path. And so let me draw it for you. So we start at C, and then we go to D, and then we go to E, and then we go back to D. But notice there's another edge going back to D, so we don't have to go back on this one. We're going back on this one. D, and then B, and then A. So because there are two edges going from D to E, we don't have to backtrack. And so this is a legal path. The next definition is a circuit, and a circuit is a path. So as long as anything that applies to a path has to apply to a circuit. The only difference between a path and a circuit is a circuit will return back to where it started. So here's an example. If we start at B, here, a path would just kind of go off and not do any backtracking and end somewhere else. A circuit, if it starts at B, it has to end also at B in order to be a circuit. So here's one. Start at B, and we'll just follow the arrows. Down to D, and then to F, and then to E, and then finally back to B. So you start and you end at B. And if that happens, you have a circuit. What about this? Is this a circuit? Same graph. ABA. Yes or no? Is that a circuit? Well, we start and end at A, right? However, if we start at A and we go to B, we would have to backtrack on the same edge in order to get back to A. And for paths and circuits, backtracking is not legal. So this would be no, not a circuit. All right, and the very last definition that we're going to get is this idea between a connected or a disconnected graph. And if this is all one graph here, this would be disconnected because we can't connect this B to something over here because there's no edge joining any of this stuff over here with any of this stuff. So this would be a disconnected graph if they were all the same. That's not the point of this problem. This over here is a connected graph because you can go from any one vertex to any other vertex. There's a path connecting any one of these with any other ones. I can get from A to B, I can get from A to C, I can get from A to D, A to E, A to F. Not necessarily with just an edge, but with a path. I can get from any one starting point to every other. Give you some examples of connected graphs and not connected graphs. Connected would be something like this. I can get from any one vertex to any other vertex by following some kind of path. Not connected would be something like this. We still have 7 vertices, but we have one fewer edge. There's no way to get from A to D. There's no path from A to D. There's no path from C to B or C to F because these two parts of the graph are not connected. Here's another example. All right, here's a graph that has 4 vertices and 3 edges. Now this vertex that kind of stands out here by itself, it's actually part of the graph, but there's no way to get from C to B or to A or to D. And so therefore this is an unconnected graph, not connected. This is an unconnected graph. There's no way to get from B to C. There's no way to get from B to D, or C to A, or D to A. Unconnected graphs. Get the idea?